Hi everybody, welcome back, and now we're going to look at how you assess normality, meaning when you look at a data set, how do you determine whether one or more of the variables follows approximately a normal distribution. And there's 5 things we can look at for that, and we've already talked about 3 of them. We can look at the histogram and see if it looks like it's approximately bell-shaped. We can look at the skewness and kurtosis values. And we can look at the box plot and see if there are outliers. Because if you have truly a normal distribution, there shouldn't be outliers. Although you can have a few and still have approximately a normal distribution. Now, the 2 we haven't looked at yet are the normal probability plot and something called the Kolmogorov-Smirnov test for normality. Kolmogorov and Smirnov were statisticians. It seems like every test we're going to do, everything we're going to do has people's names on it, so you get used to that. So since we're looking at 5 different ways to assess normality, and by the way, we won't always look at all 5 of them. For now, I want you to talk about all 5 of them while we get used to it. Later on, we'll look only at 2 or 3 of them at a time. But all of these are going to be looking at the same thing for a set of data. Most of the time, they'll show the same result. Either the data follows a normal distribution or it doesn't. Occasionally, 1 or 2 of them might give, I don't want to say conflicting information, but they might indicate not the same result. And in that case, you kind of have to take it holistically and make a judgment call. So you have to look at all the pieces together and just make that judgment call. All right, so let's talk first about the normal probability plot. The normal probability plot plots the data in your data set, in your variable, against a normal distribution. So it basically says if your data followed a normal distribution, the plot would show a diagonal line. If it doesn't, then it's not normal. I will post a video showing you how to do that by hand so that if you want to see what's going on, how those plots are created, you can. But all you really need to know is you're looking for the plot to be a diagonal line. So I'm going to pull up a data set in SPSS. So I'm going to pull up this world data set. And we will look at 2 of the variables. First, let's look at the population density. So this data set looks at, it's got a lot of different information about different countries in the world. And one of the variables we're going to look at is this population density here, which is the number of people per square kilometer. And the way you get your normal probability plot is under Analyze, Descriptive Statistics, Explore. So exactly where we've been going. We are going to move our variable over to the dependent list. And this time under plots, we're going to check normality plots with tests. And we are still going to want to turn off the stem and leaf and turn on the histogram. Right? And again, that's under plots. So we'll click continue and we'll click OK. And if we look at, well, first of all, if you look at the histogram, you can see that this is clearly not normal. You've got one huge bar here and then a couple of really extreme outliers. So you can tell it's not going to be normally distributed. But here's our normal probability plot. If this data had followed a normal distribution, we would expect to see all of these points roughly on this diagonal line that they've drawn here. But that's not even close to normal. So that's what we see in the normal probability plot. If we look at the box plot, you can see that there's a couple of countries, and we could look at what they are. I'm curious now. 87 and 79. So country 87 is Singapore, and 79 is Hong Kong. Yeah, that makes a lot of sense. Both of those being highly, highly dense places to live. Both of those are island countries, so there is no place to spread out to. So that's the normal probability plot. The next one is the Kolmogorov-Smirnov test. So there's more than one test for normality you can do. They're all a little bit different from each other, and different people prefer different ones. And there are advantages and disadvantages and situations where you might want to use one versus the other. But they all essentially work the same way. We're gonna review hypothesis testing next week. But I still want to go ahead and talk about this now. So for this Kolmogorov-Smirnov test, we are going to assume that the data follows a normal distribution unless we find sufficient evidence that the data does not follow a normal distribution. And sufficient evidence consists of finding a p-value of less than 0.05 on this Kolmogorov-Smirnov test. And so when I say small, again, that's p less than 0.05. All right, now this is on the same output that we just generated. We passed right by it on the way to the normal probability plot. These are the tests for normality. So here's the Kolmogorov-Smirnov. Here's another one, the Shapiro-Wilk. They don't always show the same results, but yeah, it is what it is. So what we're looking for in this output here is the sig. Okay, the sig gives you your p-value. And again, if you remember, small p-values indicate that you're able to conclude the thing you're testing for. So here we got a sig of 0.000, meaning that we can conclude this data violates normality. So if we look at all of this together, we've got highly skewed according to the histogram. We've got skewness value of 6.887. And we've got a kurtosis that's probably the biggest kurtosis I've ever seen, which is 49.076. The box plot shows skewness and really extreme outliers on the high side. And we should specify which way it's skewed. This is positively skewed. You can see because it's skewed to the right, this is where the long tail is. And according to the Kolmogorov-Smirnov test, shows a significant departure from normality. Now you're going to talk about that in a little bit more polished language, but here's roughly what I would say. I would say, looking at population density, according to the histogram, we can see that this variable is strongly skewed to the right. The skewness values of 6.887 is strongly skewed to the right, and the kurtosis value, 49.076, indicates a very highly leptokurtic distribution. The box plot supports the skewness, reinforces the skewness, and shows several extreme outliers on the high side. And you can even specify what those are. Finally, the Kolmogorov-Smirnov test, and you always want to, every time you state a test like that, put parentheses with the p-value, shows a significant departure from normality. Considering all of this together, it is clear that this variable does not follow a normal distribution. Now let's look at a different one. Let's look at people living in cities. So the percent of people in different countries who live in cities. All right, so let's do the same thing. Let's look at the histogram. And I would say, looking at this histogram, it looks like it might be a little bit skewed to the left. But overall, it doesn't look like it's too far from normal or too far from symmetric. The skewness is negative 0.308, and the kurtosis is negative 0.838, both of which are within the negative 1 to 1 range, indicating approximately normal. If we look at the box plot, we don't see any outliers. If we look at the normal probability plot, the points are all pretty close to the diagonal line. And on the Kolmogorov-Smirnov test, we get a p-value of 0.032, which is less than 0.05, which indicates a significant departure from normality. So, considering all of that together, we kind of have to, this is one of those times when we've got some information that's a little bit conflicting. So it's pointing to different results. I would probably go with the test for normality and say, yeah, there's a departure from normality, but looking at these other things, it doesn't look like it's a big one, is what I would say. All right, so that's it for this lesson. And, as always, if you have any questions, just let me know.